Bernoulli's differential equation is a well-known equation which looks for a specific pattern and works on a specific procedure. Check how it is performed in Engineering Math 5. Bernoulli's differential equation has a pattern which is very similar with linear DE. The standard form will have three terms, the first being the derivatives, the second term has a function of p of x multiplied by y, and these two terms are equated with the function q of x multiplied by y raised in a certain power. The set form is simplified as a linear equation with y raised to an exponent. The same pattern is observed even with dx all over dy. The Bernoulli's differential equation method is used when the exponent of y takes any other number besides 0 and 1. In the case when the exponent of y is 0, the linear format can be multiplied by y raised to n, which is 0. Y raised to 0 is just 1, which can revert back to the equation to linear DE, where Bernoulli's differential equation is no longer needed. For the exponent of y equal to 1, the linear differential equation will be multiplied by y raised to 1, which is still y. By grouping all the functions of x into one side, dy all over dx is left on the left side, and q of x and p of x are together with y. It would be quite obvious that we can cross-multiply to have y variables in one side and x on the other, concluding that the resulting equation is a variable separable equation and Bernoulli's differential equation is not needed. The procedure of Bernoulli's differential equation starts with the goal of transforming the equation into a linear differential equation. This can be done by multiplying the whole equation by the reciprocal of y raised to n, after which simplify the resulting equation by substituting a certain variable to the complicated part of the equation. The equation will eventually boil down to a linear differential equation where the standard procedure of solving is applied. With the solution, take the integrating factor, plug it into the equation, and integrate. After eliminating the integrand, do not forget to revert back all substitutions to have the general solution. Let's have the first example of finding the general solution of the equation y times the quantity of x tangent x plus ln y multiplied by dx plus tangent x dy is equal to 0. Start with transforming the given equation into the standard form. It will be easy to start the simplification by isolating dy all over dx, and that is done by dividing the whole equation by tangent x times dx. By doing this, we can simplify the function by canceling dx on the first term and tangent x on the second term. Then we get the following equation. Let's attempt to separate the first term to have p function and q function of x. The question is, are we going to multiply y into the two terms to separate them, or is it better to divide the whole equation by it? It would be wise to take note that ln of y can be reverted into dy all over y. Thus, if we divide the whole equation by y, we can have dy all over y onto the derivative later, which can be integrated into ln y. So divide everything by y to have quantity of x tangent x plus ln y all upon tangent x plus dy all over y dx is equal to 0. And now we can separate the terms. At this point, the first term can be simplified by canceling tangent x, leaving the simplified form of x plus ln of y all over tangent x plus dy all over y dx is equal to 0. Arrange the terms to take the standard form where the reciprocal of tangent x is taken as cotangent x. The resulting equation seemingly looks similar with the standard form shown earlier. So cotangent x is p of x and q of x is negative x. However, y raised to n is taken as 1, which means that n is 0, thus we got linear equation. Now that we know that we are dealing with a linear equation, let's first simplify it by substituting a variable z. Take ln of y as z, where the derivative dz is dy all over y. So we can plug these replacements into the equation where we get dz all over dx plus z times cotangent of x is equal to negative x. And this is the simplest form of the linear equation where cotangent x is p of x and negative x is q of x. So we can solve the linear differential equation with the formula of z times the integrating factor is equal to the integral of q of x multiplied by the integrating factor plus c. The integrating factor has the standard form of e raised to the integral of px times dx. We have identified p of x as cotangent of x, so by plugging it into the integrating factor, we come up with e raised to ln of sine of x. And again, e raised to a natural logarithm can cancel out, simplifying the integrating factor as sine of x. Plug this integrating factor to have z times sine of x is equal to the integral of negative x times sine of x plus c. We are now ready to integrate the form z times sine of x is equal to the integral of negative x sine of x times dx plus c. The integral of negative x sine x uses the product rule, where we keep the first term and derive the second term, sine x as negative cosine x, then add the second term multiplied by the derivative of x, which is 1. So the end function is z times sine of x is equal to x cosine x minus sine x plus c. Then revert back the substitution where we use z as ln of y. Then we get sine of x times ln y is equal to x cosine x minus sine x is equal to c, and this is the general solution for the given differential equation. Example 2. Determine the general solution of 2y prime minus y all over x is equal to 5x cubed y cubed. First, work with the standard form, thus y prime is taken as dy all over dx. Then, to isolate the derivative, we divide the whole equation by 2. Thus, we get dy all over dx minus y all over 2x is equal to 5/2 of x cubed y cubed. If we separate variables, we come up with the following equation, where it is easily distinguished that 1/2 x is p of x and 5/2 of x cubed is q of x. Then y cubed is y raised to n. Thus, we have n equal to 3. The second step is to multiply the whole equation with the reciprocal of y raised to n, and that is y raised to negative 3. And the resulting equation becomes y raised to negative 3 times dy all over dx minus 1 all over 2x times y raised to negative 2 is equal to 5/2 of x cubed. After simplification, we can work on substitution. Variable z is replaced with y, and from the equation, y is y raised to negative 2. So z is equal to y raised to negative 2. Then take the derivative, and dz is then taken as the negative of negative 2 times y raised to negative 3 dy. Note that y raised to negative 3 dy is found on the first term, so we can arrange the derivative substitution as y raised to negative 3 times dy is equal to dz all over 2. Now substitute z into the equation where there are redundant values of 2 in the denominator, so we can cancel them out. So the simplified result will show that p of x is 1 all over x and q of x is 5x cubed. With p of x and q of x already known, we can solve the linear differential equation with the formula of z times the integrating factor, which is equal to the integral of q of x multiplied by the integrating factor plus c. Integrating factor is taken as e raised to the integral of px times dx, where p of x is 1 all over x. Thus, its integral is ln of x. And again, e raised to ln will cancel out, leaving integrating factor equated to x. Plug this integrating factor into the formula to have zx is equal to the integral of 5x cubed times x plus c, which is simplified as z times x is equal to the integral of 5x to the fourth power plus c. So integrate 5x to the fourth power, where we get 5 times x raised to 5 all over 5, canceling out 5, so we arrive at z times x is equal to x raised to the fifth power plus c. From this simplified equation, we revert back to substitution, where we previously used z as negative y raised to negative 2. So we get the following equation. From here, we eliminate the denominator by multiplying y squared, so we get negative x is equal to x raised to the fifth power y squared plus c y squared, and arrange the terms to start with a positive. This is the general solution for the equation. Example 3 involves the equation xy times dx plus the quantity x squared minus 3y times dy is equal to 0. Again, start by arranging terms to have the standard form. With variables x and y incorporated in both terms, analyze which is the possible way to come up with the three terms. X squared minus 3y from the second term can actually give three terms later, so the quantity should remain in the numerator, which means we should divide xy. From the result, dx is isolated, so to complete the derivative, we should divide the equation with dy. The standard form is then noted as dx all over dy plus the quantity of x squared minus 3y all upon x times y is equal to 0. Now separate the numerators to have three terms and then cancel similar variables, which would be x from the second term and y on the third term. Arrange the terms to easily figure out p of y, q of y, and also x of n, where n is taken as -1. Move on to the next step by multiplying the whole equation by the reciprocal of 1 all over x, which is just x, to have the following equation. Substitute z, which is taken as the value of x on the second term, and that is x squared. So the derivative of z is 2x dx, where x dx is again observed in the first term. So arrange terms to have x dx is equal to dz all over 2. Plug these replacements into the equation, and to eliminate 2 from the denominator of the derivative, multiply everything by 2 to have dz all over dy plus 2z all over y minus 6 is equal to 0. This is the simplest form of the equation, and it is observed to be a linear equation, with p of y as 2 all over y and q of y as 6. Solve the linear differential equation with the standard formula, where the integrating factor includes 2 all over y as p of y. The integral of 2 all over y is 2 ln of y, so the integrating factor is e raised to 2 ln of y. In order to eliminate e, use the rules of logarithms, stating that 2 ln of y is the same as ln of y squared. Then we cancel out e and ln to give the integrating factor as y squared. Plug y squared into the formula and integrate the second term to have z times y squared is equal to 6 times y cubed all over 3 plus c. Cancel 6 and 3 to simplify the equation into zy squared is equal to 2y cubed plus c. With a simplified solution, take out z by reverting the substitution, where we use z for x squared. Thus we get x squared times y squared is equal to 2y cubed plus c.